Okay, let's begin. We had some examples to get through last time, so let's just start with those. So A, we had 0 to infinity, e to the minus x squared. Although, it's probably nicer to do it this way first. See what we're going to infinity. Just some more practice on improper intervals here. Let's start with the first 4 for those guys. Okay, how would you go about 8? What do you do?
Find the bad points.
5 points are?
Just the ability.
Just the infinity, because the exponential is defined otherwise. So, what are you going to set up here?
The limit as n approaches infinity. And then replace the infinity with the n in the term.
And now you leave the limit alone, and you pretty much do this antiderivative here. Sorry, n. So if I plug in n minus plug in 0, so I pretty much have the limit as n approaches infinity of, well, e to the 0 is 1 minus 1 over e to the n, which is going to be what? 1. Because this guy's going to go off to 0. So this guy converges. B. How do you do that one? Yeah?
Can you use comparison for the first one we did?
Okay.
So
How do
this
they
one
compare?
is, if the first one is greater, this one has to converge also.
Right, this is equal to 1 over e to the x squared. And if I wanted to compare that to 1 over e to the x dx, how would the comparison work? Well, the numerators are the same, so just focusing on the denominators, you'll notice that the denominator over here is going to be larger, especially for x greater than 1. It's going to start being a larger denominator here than there. If you have a fraction with a larger denominator, you get a smaller fraction. So this holds. So we have that pretty much. The integral that we care about here is less than or equal to an integral that we already done, and they're both greater than or equal to 0. This means that this guy here converges by comparison. Comparison to this guy. So I'm not sure at the moment what it actually converges to. Depending on how the semester goes, we'll actually maybe tell you how to actually compute that integral. But you can't compute this one as directly as this one, because probably by now you would know that e to the minus x squared has no antiderivative in the elementary functions. So you can't actually find an antiderivative here, so the best bet is to actually compare it to something that where you know how to find the antiderivative. And once the relationship is clear here, that this one converges, that one cannot pass it, so it will converge as well. Other options are you can approximate them, which the next topic we're going to do is going to be on approximating integrals. But even approximating with the infinity sign is going to be problematic either way. But we'll talk about approximating. You can approximate that integral very well, and there's even an analytical way to actually work this out by hand and know what the answer is. I believe it's going to be like radical pi over 2 or something like that. Maybe I'll show you guys how you get that. I'll need to actually explain a few Calc 3 concepts for you to know how to do that though. But yeah, we can't do it directly, but we can compare it to something, and we just have to be aware of how to make these comparisons. You can get a larger fraction by either having a larger numerator or a smaller denominator. So things like that you should keep in mind. What about C? How are you going to do that one? What are the bad points?
Infinity.
Infinity is the only one. So limit as n approaches infinity of 1 up to n of 1 minus x e to the minus x dx. Let's just get through this. You do integration by parts for something like this. Alright, let's just do tabular. Derivative of this is minus 1. Derivative of that is 0. Antiderivative of this is minus e to the minus x. Antiderivative of that is minus e to the minus x. This times that, and it takes the positive sign. So it's going to be x minus 1 e to the minus x. Plus this times that, and that takes the negative sign, so it's going to be plus e to the minus x. And then this times that, you integrate that, you get a constant, which is the plus c, so we end up with this. And now we want to find the limit as n approaches infinity of, plug in the n minus 1 over e to the n, plus 1 over e to the n, minus, when I plug in 1, I would get 0, plus e to the minus 1. What happens here? What's that limit?
Is it going to diverge because you have infinity over infinity, like for n minus 1 over e to the n? Infinity over infinity, so
Yeah, but what's infinity over infinity?
indeterminate.
It's indeterminate, which means you can't just say what the
It's
answer is.
yeah.
You can't really say it diverges. How do you actually compute it?
L'Hopital's.
You can use L'Hopital's. You can also use how various functions relate to each other. You can know that in general, this is useful for limits as x approaches infinity. We have the following. Log to the base a of x is going to be very smaller than x to the a, which is going to be very much smaller than a to the x, which is going to be very much smaller than a x factorial, which is going to be very much smaller than x to the x. And this basically says that guys to the right are much larger than guys to the left. as x goes to infinity. And by much larger, I mean really a lot larger, meaning any guys to the left, you can consider them as 0 when compared to anyone on the right as your x is going to infinity. Logs are smaller than polynomials, which are smaller than exponentials, which are smaller than factorials, which are smaller than this guy, which is just a hyper exponential. What you have here is a polynomial on top of an exponential. Exponentials are much larger than polynomials. The polynomial might as well be 0. That's going to be 0. That's also going to be 0. And so you have minus, well, basically 1 over e. So I can bring this. Or you can use L'Hopital rules. Differentiate the top, differentiate the bottom, take the same limit, and it'll be equivalent to the original limit. D. Same idea here. So x equals 0 is the bad point. It's the only one. 0 is in the middle of this, so how do I deal with that?
Split up the integral.
Say minus 1 to 0. Say 0 to 2. What you can do is find the limit as n approaches 0 from the left. As n approaches 0 from the right. Here we're going to have, well, this is x to the minus 3. The antiderivative of that, I'm going to add 1 to the power and divide by the new power. And then I'm going to take 1 and n. So basically here I will have the limit of minus 1 over 2n squared plus a half. Now of course, as this is going to 0, that's going off to infinity, so the whole thing diverges. What this guy's doing doesn't matter. Okay, so we have that. Now really this is all a matter of just, computationally speaking, improper integrals is really just us applying our integration rules while applying limit rules. But theoretically, these are very important things to be able to do. E. After a while, it should feel like almost going through the motions here. What are the bad points?
-1, 0, infinity.
And notice that this one does not apply because we're 0 or larger. So also the equals infinity, the infinite limit is going to be an issue. So we really care about the 0 and the infinity. So break this up, say 0 to 1. Plus 1 to infinity. And here we'll approach 0. ignore the limits for a second, and we just calculate the integral. How do you calculate that integral?
Can you read u sub?
U substitution, u equals what?
U squared equals x.
U squared equals x. Your 2u du will be dx. And so what you would have here is basically 2u over u times u squared plus 1 du. The u's will cancel. So you have 2 over u squared plus 1. And what does that give you? Integral of 2 over u squared plus 1.
Arctan u.
That's arctan, 2 times arctan u. So this is limit as n approaches 0 from the right of 2 tan inverse of the u, which is radical x, between n and 1, plus the limit as n approaches infinity of, again, 2 tan inverse of radical x between 1 and n. Now we have to figure out what these guys are. So, limit as n approaches 0 from the right of 2 tan inverse of 1 minus 2 tan inverse of n plus limit
Is it root n?
root n. Limit as n approaches infinity of 2 tan inverse of root m minus 2 tan inverse of 1. Okay, so tan inverse of 1 is what's tan inverse of 1? Pi over 4. So that should be pi over 2. Now as n approaches 0 from the right, so it can work in the radical, tan inverse of 0? 0. So the first limit exists, it actually approaches pi over 2. The second one, tan inverse of infinity. Pi over 2. And tan inverse of 1 is again going to be pi over 4 times 2, so I get pi over 2. So basically, we have 3 pi's over 2 minus 1 pi over 2. This guy actually converges to pi. Questions on that one? Again, it's the same process. Identify the bad points, split up your integral if necessary so that only one bad point per integral. Use limits to approach the bad points. Other than that, integrate as you normally would, and then apply the limits afterwards. All the problems are going to be like that. It's just the particular functions that happen to be involved. Every now and then you'll see a function that you can't really integrate. You don't have the rules for it, or maybe the rules don't even exist because there's no antiderivative. And in that case, your goal is to find something to compare the integral to. F. 0 to 1, x, ln x, dx. Bad points? What's the bad point here? 0, right? Because log of 0 is undefined. So limit as n approaches 0 of n to 1, we're approaching from the right, of x ln x dx. How do you integrate x ln x?
By parts.
Do by parts. Who's the u?
ln x.
ln x. So we'll have u times v. So ln x is going to be the u, the v is going to be this guy, so it's going to be x squared over 2 ln x minus the integral of phi du. So that's going to be x over 2. It's going to be x squared over 2 ln x minus x squared over 4 and then 1. Plug in 1, I get 0 minus a quarter minus plug in n, I have n squared over 2 ln of n minus n squared over 4. And what's that? So some of these are easy. That's just minus a quarter. This guy's obviously going to go to 0. So this is going to be minus a quarter minus the limit as n approaches 0 from the right. I can even factor out the 2 here, of n squared ln n. How do I compute that limit? Yeah?
Negative infinity.
Negative infinity? Why?
For the graph ln.
Okay, but there's an n squared multiplying it.
Oh, yeah, 0.
So now your answer is 0?
Or
Why?
infinity, yes.
In the, well, it's
0
indeterminate.
times infinity.
Yeah, indeterminate is the thing, because this is approaching 0 times negative infinity. You have a 0 times infinity here. What do you do in that situation?
L'Hopital's rule.
L'Hopital's rule. How can you apply L'Hopital's rule here?
Use the product rule.
No? Do we never remember what L'Hopital's rule says? Specifically?
Can you rewrite it as ln over n to the negative 2?
You can do that. Because L'Hopital rule does not apply to products, it applies to quotients. It applies to limits that go to 0 over 0 or infinity over infinity, none of the other indeterminate cases. Now if I look at this, what's going to happen is ln is going to infinity and 1 over n squared as n goes to 0 is also going to infinity. So this means I can use L'Hopital's rule. So that's what I'm going to apply now. So L'Hopital's rule tells us that once a limit goes to 0 over 0 or infinity over infinity, the limit is equal to the limit you would obtain by just differentiating the numerator and the denominator separately. So it's not a quotient rule or anything like that, it's a separate theorem altogether. Now, this one, this is 1 over n cubed, you would flip and multiply. So you have minus so you'd have 1 over n times minus n cubed over 2. This leaves you with n squared, and your n is actually going to 0. So that all goes to 0. So we end up with minus a quarter as the answer. The idea here is that the n squared is approaching 0 a lot faster than the ln is approaching infinity. So the polynomial here again beats the logarithm. But yes, L'Hopital's rule, all that limit stuff from Calc 1, you need to remember all of it. It's going to be assumed that you know all of it. So I believe I was looking at this with someone earlier. I think teach the general approach to limits, and I believe lecture 17 is when I cover L'Hopital's rule. Don't quote me on that, just read the description, the title, and you can find them, but I think it was 4 and 17. Make sure you know everything that was said in those videos. Let's move on to G.
Sorry, I just have a quick question on the last one. Do you have to do L'Hopital's, or could you just think of the n squared overpowering that ln n, like you said, so you would just know that approach is 0?
I'm hesitant to say no. The rule I gave you really applies for when x is getting larger.
Okay.
The inverse relationship, I don't know if it works out in all cases.
Okay.
I'm hesitant to say. I think it might work out in the same way. You can invert all the relationships I mentioned there, so that's for sure. So by me saying things like log to the base a of x is much smaller than x to the a, which is much smaller than a to the x, which is much smaller than x vector, which is much smaller than x to the x. It's true that you can reverse these. So 1 over this should be it's kind of weird to write it like this though. I don't want to say that. But what I would say is the guys on the right would decrease faster. So when you just leave the functions as they are, the ones on the right increase a lot faster than the others. Take the reciprocals, they'll decrease faster than the others. So that's also true. But again, here I don't have the 1 over ln, so I don't want to say that it will work in that case as well. But technically, you can think of this as 1 over a polynomial going off to 0 versus a logarithm that's going off to infinity. Cases like this, it'll work. For a polynomial and a log specifically, yes. But there's probably some combination I'm not thinking of where that will work. I'll just do the L'Hopital's rule. It's not that hard here. This one, so what's the bad point here?
Infinity.
Infinity is a bad point.
And 2, but 2 is not in that.
2 is also a bad point, x equals 2. Anything else that's larger than 2? No, right? I mean, your x can't get too small because there's a square root. So your x has to be 2 or bigger, and nothing larger than 2 is going to be a problem, so the infinity is the only problem here. So as n approaches infinity of 3 to the n, alright, this is x minus 2 to the minus 3 over 2 dx. To do a u substitution here, your du would equal to dx, so you can kind of just do the power rule with this guy. So you add 1 to the power, divide by the new power. So you get that, and so now we'll have a limit as n approaches infinity of minus 1 over 2 radical of n minus 2 plus.
Wouldn't you multiply by -2 and not -1/2 when you're doing?
Add 1 to the power, divide by, so the power is 1/2, divided by 1/2 is multiplying by 2. Yes. So this would be 2 over that, plus 2 over, if I plug in 3 here, I just get 1. And as this goes off to infinity, that goes off to 0. that just settles that too. Let's start to speed things up here so we can get through the next section. Tons of examples. So the quiz tomorrow is going to cover Weierstrass substitutions and improper integrals, all sorts of versions of it.
Is it partial fraction decomposition too?
Incidentally, wherever incidental. So I'm not testing you on partial fractions, but if I give you an integral where you need to use partial fractions to do it, I expect you to be able to do it. So, but the test is, I'm gonna, in terms of like the general problems I'll ask you, you know, like when I ask you the general formulas or general concepts, I'm gonna be asking you those about improper integrals and Weierstrass substitution. And then I'll give you about 5 integrals to do for each. I think I asked 1 Weierstrass substitution integral and 4 improper integrals. So, yeah, we need to be able to compute these guys quickly. So, what's the antiderivative of 2 to the x? In fact, negative infinity here is the only bad point because 2 to the x is exponential, it's always defined. So integer 2 to the x dx. Antiderivative of 2 to the x. You guys need to remember that. Plug it into 0, we get 1 over ln2 minus plugging into m, I get 2 to the m over ln2. As m is going off to infinity, this guy is going to go off to 0 if it goes off to negative infinity. That's 10. Because 2 to the negative infinity goes off to 0, so this gives you 1 over ln2. This is a polynomial times an exponential. They are defined everywhere, so no finite bad points. The bad points here are the infinity symbols, so I would split this up. First, the bad points with limits. What's that, minus a half e to the minus x squared? So the derivative of that is going to be the derivative of the power, which is minus 2x times the original function, and yeah, that looks right. So here I would have the limit as n approaches negative infinity of minus a half e to the 0 plus 1/2 e to the minus x squared to the minus n squared. Now as n is going off to negative infinity, we're squaring it so it becomes positive, and then I'm raising that to a negative power, so this whole thing is going to go off to 0 and plus minus 1/2 e to the minus m squared plus a half. For the same reason, this is going to go off to 0. So we end up with what here?
Yeah.
Which might seem crazy to you, but just remember that there's an x there, and you're going from negative infinity to infinity. So this guy's always outputting positive numbers, but that guy's outputting negative numbers, and you kind of have an odd kind of shape going on here, an odd graph, if you remember that from top one. So the area on the right is equal to the area on the left, it's just that one is above and one is below. So they kind of cancel each other out. This is an odd function. So we know that odd functions on balanced intervals cancel each other out. Whenever you have infinity though, you still do want to check it very carefully. Approach these back points. Let's see here. So I had one more example that I gave you guys, but I threw in two more for good measure to make sure that we're covering all our bases. So let's finish the last three and then move on to something else. I'm sort of getting bored with integrals now. Okay, we have J. Infinity y cubed minus 3y squared. Okay. Okay, we're going to do those and then we're going to jump into approximate integration. Over here. Okay, so J isn't that bad. Polynomials. So the only place they'll mess up is at the infinite limits, so I'm going to do the same kind of idea. So n goes to negative infinity, negative to infinity. Plus n goes up. N up to say 0, and then n goes to positive infinity from 0 to n. This guy, what's going to happen here? Well, first you're going to get 0. Minus, well, we will plug in n to the 4th over 4 minus n cubed. One way you can think of that is n cubed. Minus n cubed times n over 4 plus 1. So this becomes negative infinity times positive infinity, which is not indeterminate, that's actually just negative infinity. So this one diverges. As you probably have guessed, this one is an odd function, so that's going to cancel itself out. But the square, the parabola, well, it's upside down. You'd have an infinite area that's increasing off downwards. So that diverging to negative infinity doesn't, shouldn't surprise anyone, I don't think. What about this integral? So, thinking about Okay, ideas for this one? Well, -1 is a bad point and infinity is a bad point. -1 does not apply, so infinity is the only thing I have to worry about. How do you compute that integral? Think about what would you do in these scenarios? What are you guys thinking?
Can you factor it?
You could. The x cubed plus 1, you mean?
Yeah.
Yeah, you could do sum of squares, x plus 1 times x squared minus x plus 1. Does that actually help you? Well, the answer is these integrals are very hard to compute. I would think comparison theorem. Think about that in preparation for tomorrow. Let's move on. You guys try this. Comparison theorem is probably the way I'd go because we haven't learned anything that will allow us to integrate these guys. At least not without a lot of pain. Move on to approximating integrals. Conceptually, this is pretty much the same thing we did in approximating definite integrals. Same thing we did in Calc 1 when we were doing the right-hand rule and the left-hand rule and the midpoint rule. The only difference is now I'm going to tell you about a couple of error bounds that we can have on these approximations, and I'm going to tell you about 2 new techniques. So this is pretty much picking up where we left off in Calc 1 regarding the right-hand and midpoint approximation methods. So recall the idea here was we want to approximate the integral from a to b of f of x dx. And in general, you'd only do this if your f of x is really hard to compute, but in Calc 1 we might have given you even some very integrals that you could compute very easily by hand, but the principle was important. So you have your function doing its thing, f of x, and we had this from a to b, and you wanted to approximate this area. One way we did this was we sliced this interval into n quote-unquote subintervals, and we started labeling certain things. So the a we called x0, then this is x1, then x2, then x3, blah, 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 all the way down to the b, which we called xn. And then we set up the fact that these guys here are of equal distance, which we called delta x. So each subinterval, as they were called, had the equidistant. They were all of equal length, which is going to be b minus a over n. And then we basically had to have a formula. So what we did, I'm just doing an example of like a left-hand approximation here. So basically, here we had like f of x0, f of x1, f of x2, etc. And the idea was, we're going to take the height times the width of all the rectangles, add them all together, and this was an approximation for the area under the curve, and the more rectangles we used, the better the approximation got. So some equations that are still true. So pretty much exactly what we memorized from Calc 1 is that we find the delta x by taking b minus a divided by n, where n is the number of subintervals, and also the xi is going to be a plus I delta x, which is given by that. So you start with the a, and then you keep adding the length of the subintervals to get each xi. And basically, the area was approximately equal to the sum of the f of xi times delta x. I goes from 0 or 1 up to n, where the xi are chosen based on a rule, the midpoint rule, or the right-hand rule, or the left-hand rule. So now we're going to talk about some how good approximation this kind of thing is, but we're also going to introduce two new methods that in some contexts will actually converge to an approximation that's better, much faster than any of the rules that we've learned before. Here are two additional rules. So midpoint, right hand, left hand, you still need to know those, and it's fine for me to actually ask you about them and test you on them. But we have two additional rules. One is called the trapezoid rule. Now, this guy works by approximating the area under the curve with trapezoids. Under quotes, x with trapezoids. So, the idea here being, here's a curve, here's A, here's B, and I can split this up into some subintervals, let's say just for illustrative purposes, illustration. So we set up the subintervals we'll have these things hitting the curve at certain points. And what we actually do is we just actually connect those points with a straight line. So, and these, by doing so, we will create trapezoids. And the idea is, rather than cutting straight across, we actually get a lot more of the missing area by actually connecting the points directly via a straight line. So if we were to do something like a left-hand approximation, the left hand would miss all of this area, but the trapezoid rule won't. It'll include more of the missing area by doing a trapezoid. So we have a bunch of trapezoids here. Now, if I start to actually label these guys, see, this is your A equals x0, this is x1, this is x2, this is x3, this here is x4. What would the actual thing look like? So you can want to recall, if you have a trapezoid like this, where the height of this is x, the height of that is y, and the length of that is z, and the area is 1/2 the sum of the two parallel sides times the distance between them. That's the area of a trapezoid. And so basically, we apply that formula to each of these guys. So in the above, basically what we would have is that the first trapezoid, second, third trapezoid, I should just write the three, got the idea. Fourth trapezoid. Basically, the height here is going to be f of x0, height here is going to be f of x1, height here is going to be f of x2, height here is going to be f of x3, height here is going to be f of x4. And so for the first trapezoid, it is 1/2 the sum of the two parallel sides, so this is f of x0 plus f of x1 times the distance between them, which by our definition is delta x. I can write this delta x in the front, and continuing like that, I would have delta x over 2 times the sum of those two parallel sides. That's f of x1 plus f of x2 plus, here I can have delta x over 2 times f of x2 plus f of x3 plus I can have delta x over 2 times f of x3 plus f of x4. What you notice here now is your delta x over 2 is a common term that you can factor out. You would then be left with f of x0 plus, notice that you'll end up having 2 f of x1s, you'll also have 2 f of x2s, you'll also have 2 f of x3s, you'll have 2 of every guy except the first and the last guy. So it's 2 f of x1 plus 2 f of x2 plus, keep going until you have 2 times f of the second to last guy. Let me write this out. Plus 2 times f of x3 plus f of x4. And that's the formula. Your delta x is going to be given by the same b minus a over n. This still applies. And we have that. So this leads to the trapezoid rule. Integral from a to b of f of x dx may be approximated using n trapezoids via the integral of this going to be approximately equal to delta x over 2 times f of x 0 plus 2 f of x 1 plus 2 f of x 2 plus 2 of every one except the first and the last guy. And now, if you look at your handout here that I gave you, that's the formula that we have here. So that's how we actually got it. We just added up all the areas of these trapezoids. The right hand, left hand, and midpoint rule, as I mentioned, I derived those back in Calc 1, so I'm not going to go over those. But let's actually talk about Simpsons Rule. Where did that formula come from? Simpsons Rule is really cool. This guy uses parabolas. Simpsons Rule. This approximates using parabolas. One special note about Simpsons Rule, you need to have an even number of subintervals. And the reason why is because to pretty much come up with a parabola, you need more than 2 points, you need 3 points. Right, so for a straight line, to determine a straight line, you only need 2 points along that line. To determine the equation of a particular parabola, you will need at least 3 points on that parabola. So because we have to set things up in groups of 3s, it turns out we always have to have an even one, because the rightmost point is going to give an extra 1 after we group all the others to it. And so the idea here so basically what's going on is you might have your function doing whatever it does. Let's say you're here at A, and here you're at B. We're going to create the subintervals. Now we locate a parabola with 3 points. So I'm going to take this point, and that point. And then I'm going to do another parabola, say over here, with this point, that point, and that point. Then I can do another one, say with this point, that point, and that point. How many do I have here? 1, 2, 3, 4, 5, 6. What's that here? So basically what Simpsons Rule goes in and does is it connects these 3 points with a parabola. And then it defines the area under that curve to be the area under that parabola. And then it uses the next 3 points and it creates a next parabola passing through those 3 points. And then it finds the area under that parabola over that interval. And then it's going to connect the next 3 points via a parabola. And the idea is, because this is even curving, it would get closer to a curved shape. And you'll find the area under that parabola, and so on and so forth. So using 6 subintervals, I can approximate the area under the curve with 3 parabolas. And so because I need 3 points, I need 2 subintervals to cover a single parabola, which is why I need an even number of parabolas. I need an even number of subintervals. Now, how do you actually figure out what the heck that should look like? How do you find the area under this parabola? Well, how do we do it? We start with the following. Imagine that your parabola is actually centered at the origin. Say it goes from a distance minus h to h, and that's going to be 0 in the middle. Now, this is the distance delta x, but I don't want to write delta x over and over, so I'm just calling it h. So that length is delta x. So wherever you see h, I'll eventually replace it with delta x. As well as I'm going to call this x coordinate is x1, x0, this is x1, this is x2, and the corresponding y values, this is going to be x1, x0, comma y0, and this will be x1, comma y1, and this will be x2, comma y2. And so start with finding the area under this. Now the idea is, once I can find the area under a parabola in this position, all I have to do is slide this axes along all the parabolas, and I can figure out how to find the area under those. So what I do, what Simpson did, he basically said, let the parabola be, say, p of x equals ax squared plus bx plus c. Then this means the area under the parabola is going to be the antiderivative from minus h to h of ax squared plus bx plus c. So that I can find this is ax cubed over 3 plus bx squared over 2, which by the way, that's going to cancel. That's not a function over a balanced interval, plus cx between minus h and h. So your area is going to look like ah cubed over 3 plus ch minus, you're going to plug in the negative h's, they're all going to become positive, so you end up with 2ah and 2ch. That's going to be the area. Now we want to look at that in terms of the actual coordinates, because that's how we're going to be splitting things up. We're going to be finding these x values and their corresponding y values. So what do we do now? Well, p of 0 equals y1, because x1 is 0. That basically tells you that c, the value of c is y1 in this parabola. Also, here's what we also know. If I look at p of h, that is going to be ah squared plus bh plus c. And if I look at p of minus h, this is going to be ah squared minus bh plus c. And I can add these two equations, so that's equation 1, that's equation 2. If I add them, 1 plus 2, the BH's are going to cancel, so I don't have to actually worry about the B just yet. And so what I would have here is P of H is actually Y2, and P of minus H is actually Y0. And so what I end up with here is basically 2ah squared plus 2c. And the 2c I know, so y2 plus y0 equals 2ah squared plus 2y1. And so basically here I can get my 2ah squared. That is going to be actually equal to, well, I'm going to subtract this, so that's going to be y0 minus y1 plus y2. We're getting everything here? So I know 2ah squared is that, and I know that my c is actually y1. So now what happens is, now going back to the area, we end up with the following. The area under this parabola is going to be equal to the area here is going to be equal to 2AH cubed over 3 plus 2CH. AH cubed, no idea what that is, but I do know what 2AH squared is. So what I'm going to do is I'm going to factor out h over 3. That will leave me with a 2AH squared. And then by factoring out the h over 3 over here as well, I would end up with 6c. Right? That looks right. I think one of the numbers are off here, but let's actually start putting in. So this gives me h over 3. Yeah, this should be 2 minus 2y1. Okay, now I think it's fine. So the 2AH squared is y0 minus 2y1 plus y2. And the 6c, well, c is actually y1, so that just becomes 6y1. And so we end up with h cubed of y0 plus 4y1 plus y2. Or more generally, delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. Now when you add a bunch of things like that together, what you're going to have is that the left end of the next point is going to be overlap with the right end of this point, so you're going to get 2 of those guys. And then they're going to have a 4 in the middle, then you're going to get 2 of these guys. So what you end up with ultimately, which I guess next time I can write it out, is you have alternating 2s and 4s, starting with the 4. You will end up with the A equals delta x over 3. It's going to be f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus dot dot dot, and it alternates all the way to the end, so it will leave us with 4 f of x n minus 1 plus f of x n. 2, 4 will alternate, starting with the 4. Because I just add a bunch of these things together. Delta x over 3 times y0 plus 4 y1 plus y2 plus delta x over 3 of y2 plus 4 y3 plus y4 plus so on. So these 2 guys double up, and then the other guys in the middle gets to the 4th. So when you look at the next formula in your handout for Simpsons Rule, you'll notice that pattern. This 4, then 2, then 4, then 2, then 4, then 2, and you end up with that formula. So that's where the formulas come from. You don't need to know how to derive it, I just thought I'd show you. But all you're going to need to know is know the formula and be able to do these problems here, which we'll start next time because we're out of time. But it's going to be like plug and chug arithmetic. Kind of like midpoint rule and all that stuff from top 1. So review those and you can go through this. Actually try these problems before we actually do them in class. That would be very helpful. Yeah.
So are these going to go on the quiz tomorrow? Or?
No, quiz covers last week.
Okay.
So I might say something here on the bonus, but you're not required to know it.
Okay.
The quiz covers Weierstrass substitution and improper integrals,
Okay.
including the comparison theory, because I started to ask.
Okay.
So know about all of that stuff. If you have time left over, you can look at this.
Thank you.
Thank you.
Okay.